Okay, so we've been talking about here this idea of memory management, and we're starting to look at it with the concept of how we handle array lists. Now, a couple of things on here that on this slide I want you to pay attention to. Number one, your discussion question this week is actually related to this. It's asking the question of what is a singleton class and how would you use it, and this is actually a design pattern used in Java. Keep in mind that memory is finite. Everyone knows that your hard drives and the RAM on your computer cannot hold the world's data. It's just that's not enough, right? So memory is finite. And that means that we need to think about how we use objects. When we think about numerics, for example, a byte will hold 1 byte. And it stores numbers between -128 and 127. So if there are instances where you want to use declare an object as type byte, and you know it's only going to be within that range, it makes sense to create that type of object. If in short, it's the same idea with a short. It can hold a number that's negative 32,068 up to 32,767. Int 2,147,483,648, right? And that number may seem really large, but when you're actually looking at ID numbers, that number won't actually hold. You'll need even larger numbers. In most systems, we declare IDs as longs because long is, I don't even know what that number is. It's awfully large, right? Same thing with float. You'll notice that float corresponds to int, right? They're both 4 bytes. Double corresponds to long. They're both 8 bytes. A Boolean is only 1 bit. It's either on or it's off. On or off, which makes sense, true or false. And then, of course, a char is 2 bits. And chars are designed to store ASCII values. All right, keeping that in mind, when we create objects, we want to be thinking about memory is finite. So I want to use data types that represent only what needs to be used, right? So if we're storing very large variables and very large quantities, it can create bottlenecks. And this is the example I was trying to convey with, say, an array or an array list. If I have large objects stored in a very large array, and I have to do maintenance operations where I'm inserting into the array at a certain point and removing objects at a certain point, that's going to create performance bottlenecks because it means that your processor has to go on one side and retrieve the memory, pull it into the processor, switch it, write it back to the memory, and do all of these things back and forth until it gets the RAM where it's written to in memory at a certain level, right? So it affects performance. Classic contiguous operations. 0, 1, 2, 3, 4, right? So we're using the array index to access that location. And when you need to do operations on an array, where you insert an object and remove an object or replace, you have to think about how you're going to either grow the array or shrink it or what you're going to do. And when you get to an array list, it's the very same idea. Now, the array list itself, it has a couple of helpful methods. You can say list add, and this will always add new objects at the end of the array. Okay? Whereas if I use list add I object, that's going to do an insertion. I represents the index that we're going to be accessing. So if I happens to be some number like 2023, and I add that to the array, that means every item after that to the right has to shift. And that takes time and memory. We have the same idea with list remove. I can remove an object, and list remove always removes from the end. List add always removes from the end. However, list remove I object is list remove I and no object is taking an object from that indice from that point. Okay. All right. Now this gets to an interesting idea. I started this conversation a moment ago by saying, how about we store items all over the place? Or you're like, Mr. Rogers, that's not a list anymore. Well, see, our classical understanding of a list is how we typically create lists. But let's say that Leslie, in your room, that you have a very clean room, right? No. Oh, okay, I'll call on someone else. I'm messing with you. This is actually a good example, okay? This is a good example for anyone. In your room, you create a note, and you say, on this note, the name of something, an important date, and then you have a reference that points to where the next note is located in the room. Now think about that for a moment. It doesn't make a lot of sense in the classical sense of a list, but when we think about contiguous operations, it makes a lot of sense. Because now if I move something and change it at that location, it doesn't affect the locations around the room. The room being RAM. It means that it's very fast. I can go in and move an object and take it out, and it hasn't affected anybody else in the room. Because the memory reference is not contiguous. It means that I don't have to gather everything back in the same set of cells in memory and shift it around. It's kind of randomized in some sense. Now this comes full circle to how we create objects. So when we say person Jack equals new person, I'm not specifying where in RAM to store that. I don't care, right? If I was creating an array of person, well, then it's a different matter because I know that it's going to be contiguous. But this is where we get to an interesting idea, and this is called the linked list. And a linked list is, you all can read that, right? A linked list, I'm going to take this and dump it into IntelliJ in a second so you can. A linked list uses this idea of elements being stored around the room. But we don't necessarily do that on our own. We allow the computer to handle that for us. And so what I'm going to do here is I'm going to copy this code. And let's see. Actually, I can't even tell what that says right there, but we'll just kind of come over here and create a new Java class, and I'm going to call it node for right now. And then I'll fix this in a second because I can't remember what this was. Int node. Okay, int node. So we're going to rename int node. All right, I'm going to maximize this so you can see it. So here's a class we created, and int node is just the name of the class. It tells me that it's going to store an object of type int. And it's not really an object because it's primitive, but keeping that, just put that on the shelf for a moment, right? We know that objects would be the uppercase integer class. That would be the wrapper objects, all right? But this is storing a data value called of type int. And it has a second private member variable. What is the type of that second private member variable? What is the type?
Int node.
All right. Does anyone see something interesting here? Int node is a reference to itself, or we would think it is. It's actually using the class name itself for creating another memory reference. And this memory reference we've called next node pointer. All right? All right, so we have a standard constructor, public int node, and we set the data value. Here's data value, right? We're setting it to default so that when the constructor is called, automatically data value is going to store 0. And in the constructor for int node, we're telling to go ahead and set this private member variable to int node to null. Okay? Then we have another constructor, and this one takes a value and called data init, and it sets the data value to that value, right? And again, the next node, which is the int node itself, is set to null. Then we have another one, another constructor that we're overloading. So technically, when we create this object, we could create it saying new int node, and we could use 3 different constructor possibilities here, right? One using the default, one using passing in an int, and the other passing in an int and an int node, right? Then we have a method here. And in this method, we create another int node. And this int node is actually just a temporary placeholder. It's like the card trick where you have only 3 cells and you have to move things around, and so you have one empty cell that you can move something to, but you can't take them out, so you have to shift them around, right? You're shifting things around in these cells. So this int node is the empty cell that we're going to use for shifting things around temporarily in memory. And insert after is the method name, right? And it's saying I'm going to accept something of type int node, and this is the node location. And so this is being assigned to the next node. Okay. Next node pointer is being temporarily put to the temp node. And then we're saying take the parameter from here and assign that to the next node. And then once we've done that, once we've swapped them, now we've created that empty space where we can go ahead and do the final switch for adding the next parameter value. And that's where we say node lock is going to be added to, or excuse me, temp node will be added to the next node. Okay, that's how we're switching things around. Now that conceptually is going to be hard to think about, but when you get home tonight, create yourself a little, 3 items and think about how you can move objects around in these 3 little squares, and you only have 2, and you just need to think about, okay, I'm going to move this object to there and this object to there to finally get the beginning object to the right location. Okay, essentially trying to switch 2 objects. How do you do it? Well, you have this third empty object. So I take one, move it to the empty object, I take this one, move it to there, and I take that one and move it back to the first. That's how I'm doing the switch. Does that make sense, or am I still confusing everyone?
It's kind of like, what is that puzzle thing with the tiles where you move the tiles around?
Yeah. Yep, exactly like that. You have an empty spot. You got these 2, you need to swap them. So you take this one, you move it to over here. You take the first one, move it to the second. You take the third one and move it back to the first. So that you've effectively swapped locations, but you're not losing the contents of what was in memory. Okay? That's what this method is doing. And then we say get next, which gives us the pointer to the int node. But you notice that it returns the node. And then we have print node data. Okay, let me go back to over here and grab this. This is called custom linked list. I go back to my project. I'm going to create a new class. I think it was called custom linked list. And I'm going to paste it underneath to make sure I got the spelling right. Custom linked list, custom linked list. Okay, good. Keep in mind that the name of your class must always match the name of your file. Okay? Right? That's important. All right. So let's look at the code in this class here. The code in custom linked list is using the int node. This is what we specified over here, this class. I have a header object. I have an int node called current object, and I have an int node called last object. And I'm initializing my header object to be an int node of -1. And this represents the beginning of the list. And then I'm also initializing my last object by pointing back to the header object. Now, don't get overwhelmed here, okay? Because remember, we're going to create now a collection of 20 objects using just these 3 in memory. And how we do it is by looping. And all we're doing is, notice at the beginning here, we take the current object and we instantiate it with a new int node. So that as soon as you call that constructor, I've now thrown something up in memory. Not puked. I've put it in memory, right? Okay, I've put it on the wall in memory. And as I iterate through this loop, I'm putting new objects up in memory. You guys understand? And the reference to each object in memory is using this method insert after. Now think about that. Insert after. So now I'm creating this object in memory, and I'm creating the reference by adding it to the current object. So last object, if you remember up here, last object is initialized with header object. And I'm inserting it, and I create a reference, and then I take the last object, and then I'm assigning current object to it, right? So then I get down here to the bottom, and I'm going to loop through my objects. And all I'm going to do now is I'm going to access those memory locations by calling print node data. I'm going to access those memory locations by calling get next node. And get next node is going to be able to look starting at the top and go, okay, this node references this node, which references this node, which references this node, which references this node. They all exist in memory. All right, now here's the catch. And this is why I'm taking so much time to really talk about this. We're used to thinking about things in lists, but remember, this is not a contiguous collection of data. It's more like this node refers to this node, which 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 refers, right? It's all over the place on that little stick of RAM. It's all over the place. So the benefit of this type of data object is you can do inserts and deletes without having to change or shift the data in an array, because it's not an array. It's just a memory location. Okay, if you understand, raise your hand. I don't want you to feel bad if you don't, because this is a complicated idea, okay? But if you get it, or you understand the idea, the premise behind it, this is important. All right, let's go back and notice what we're doing here. We're going to set the math random, and we're going to get this number, right? Between 0 and whatever, 99,000. And we're going to convert it to an int, and then we're going to store that int in code. All right, so I'm going to go back here, and let's see, where's my custom linked list? I'm going to come up here, and we're going to run it and see what happens. We have 20 objects that are created. First object is -1. Next object is this. The next one is that, and so forth, all the way down. They all contain this different random number. But based on the code, as it gets the next object, it passes into current object and stores it in memory until we get to the last object. And that last object created doesn't insert a new node object. And so that node object will be null, which is what it checks for here. Current object, as long as it's not null. You guys understand? Okay. Now, there is a lab in your textbook where you're going to have to do this. Zach, your look on your face was priceless there. You're like, oh, man. Okay, there is a lab in your textbook where you're going to have to do this. Now, the reason we're spending this much time on this, because I'll give you an example. A number of years ago, I did an interview for Amazon, and they began to ask me this very same question. I said, all right, Mr. Rogers, how would you handle this scenario? And we talked about a number of different ways of how you would handle these large collections of data. One of them was using a hash map, which is a key value pair. We'll talk about that in a couple of weeks. And the other one was using this very idea right here, next nodes, okay? Linked nodes. All right. Let's go back to our slideshow here. We have about 15 minutes. All right. That is memory management. There are other items that you're going to read about this week. One of them is garbage collection. Okay. I've talked about garbage collection before. This isn't where Art Man comes to your house and collects the trash. Okay. There is no, well, I mean, there technically is an Art Man in Java, but we call it the garbage collection, right? And it's based on the idea of when things go out of scope, all right? So let's take a quick look and talk about scope. Let's see. I think this example here might be good. Let's just create a new class. All right, I'm going to call this memory scope. And I'm going to create a global object first. Private int age. And then I'm going to create a method, public calculate I don't know, calculate birth, and we'll give this a current age. Okay. All right. Starting off with the basics. When I instantiate this class, okay, the scope of the age variable is global. Okay? And it's global because it's class level. So when the garbage collector comes by my memory scope class here and says, okay, what are we done with? It will not touch the age variable until the memory scope class is out of scope. Okay? The age variable is the last thing it gets rid of. It cleans it up off of the RAM on your PC. And it does that when the memory scope class is about to leave. All right? So before we do that, though, let's create another variable. In here, we'll create a date. Oops, wrong kind of date. It's data. Okay, we'll create a date. And I'm going to call this now equals date, or is it instant dot now dot. And I'll just do it this way. New date. Okay. All right. And then I have current age. I'm just going to do something with it for right now so we can have some different variables to look at. All right. And then I'm going to create a public static void main method. And in this, I'm going to instantiate my memory scope equals new memory scope. And I'm going to say ms calculate age, and I'm going to say 35. Okay, so let's step through it. When the program runs right here, the first variable that's instantiated in memory is memory scope. And this variable is going to stay alive until the program ends. Garbage collection will not touch it. The next variable in memory scope that's instantiated is the age variable. And age will stay alive because it's global to the memory variable, memory scope class. It'll stay alive until the program ends, meaning garbage collection is not going to take it and remove it from RAM. However, we call this method calculate birth when we pass in the variable 35. And then down here, I do two things. I create a now method and a current age method. The scope of these two variables is going to die very quickly. It only lives for the present moment that calculate birth is called. And when calculate birth is done, those variables disappear from memory and garbage collection comes in and gobble, 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 just eats it right up and frees up your RAM, okay? These are some concepts that you're going to be looking at in your Zybooks textbook. You also see it in the quiz. By the way, the quiz this next week, I've reduced it. There's only 18 questions. I thought there would be shouts of hallelujah in here. Okay. Make sure you look at these questions because you will see them again. Next week, we're supposed to be taking mid-quarter 2 exam. So, you know, we're at the halfway point now in this class. And 2 weeks from now, there's spring break, I believe. We won't be meeting for that. And then 2 weeks after that, or 3 weeks after that, the class will be coming to an end. So this last 7 or 8 weeks are just gonna zip by, okay? All right, so this is on garbage collection. And you'll see that in your Zybooks. All right, let's go back here. Chapter 9, we get into something called output streams. And this is important. We've used the system out print line quite a bit, and we use system in quite a bit. So an output stream it's just a class that supports output. And the output stream, it's basically for writing a sequence of values or bytes to something. Now, I mentioned before, every class by default has a print, toString method, right? So I'm going to call the toString method inside of my print line here. So I'll say ms toString. Because I have not overridden it, what it's actually going to give me is it's going to give me a hexadecimal location of where this object is stored in RAM. And there's actually programs out there that will calculate this and tell you the actual memory registry location. If you want to know that, you know that's kind of cool, but otherwise it's not very useful unless you're going to do some type of low-level programming, right? But you can actually find out where it's located in memory. So if we run this program, we're going to see that the toString gives us the hexadecimal memory location for the memory scope object. And if we look at it, we can see it's right here. Memory scope is located at, just like you have an email address, memory scope is located at this hexadecimal location. Okay, hexadecimal. Now, when we're doing an output stream, we're writing the sequence of bytes to a particular location. And this is output stream by default. For example, system out is predefined in the output stream reference. When you're using, later on, if you were to get into things like web development, some of the HTTP print protocols, print drivers, all of those use the print stream by default. And you can actually write low-level print streams and print web pages. So you can actually, go to your browser, go to whatever port you're specifying for your print stream, and actually spit up a web page, right? And a lot of the higher level Java Enterprise Edition programming does that for you, so you can actually create web pages and do dynamic stuff in Java. It's really cool stuff, and that's actually where a lot of money could be made in the job market. Okay, so this is the system out, right? Then we also have the input stream. Just like the system out, we have system in. System in is used for reading from the keyboard, okay? And where do we use the system in? Where have you used it quite a bit? Scanner, right? Because you're telling the scanner, listen for input, right? At a low level, everything, whether it's input stream or output stream, it's using a byte stream. And you guys, just like me, we don't read bytes very well, because we're used to, if I just gave you a series of zeros and ones and said, okay, here, tell me what that says, you'd be like, I don't know, right? But at a low level, these byte streams are converting what is coming in, and it's using the byte stream to do that. Now, system in takes the first 8 bits of an ASCII value variable and it puts it in this buffer. A buffer is basically just an array. It's taking and putting in an array. All right. Opening and reading from a file, and I'm gonna stop here because let's pull this up. We'll create a sample class here real quick. I see some of you are getting kind of tired, and don't lose heart yet. Okay. Okay, let's take a look at this class here. In this instance, we have a public static void main method, and we're going to throw an IO exception. This is very important. Anytime you're going to be reading using a byte stream, you need to throw the IO exception, just in case if the file doesn't exist, it'll throw an exception. If there's any issues with reading the file, you have to catch that exception. And we're not at the point of talking about trying and catching exceptions yet, but this is important. We declare a variable called file input stream and file labeled byte stream. It equals null. We create our scanner class, and we're going to call this variable the NFS. We're initializing it to null for right now. And then we have file num1 and file num2, because we're going to read the data from a file. And then we have the file input stream for the file itself. Okay? So what I'm going to do, I'm not exactly sure here. We'll just call this num file.txt, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1. Save that. This file could exist anywhere on the file system, but because I'm referencing it locally, I'm going to keep it in the same source folder. Okay. We're going to create this file input stream. The file input stream takes a parameter of type file or of string for the file location. If you were to actually dig into this, you'll see, that the string name, where is it at? The string name is actually going to be the URL, and it'd be the directory plus the file name, right? Or you could create a file object and pass that in. So here I'm using just the file name itself. I take the file stream object, I'm going to pass it into the scanner. Instead of a system.in, I'm passing the string, it's a file stream object, into the scanner. And now my scanner object is ready, and I'm basically just going to read from it. Next int, next int. And it's going to read those two integers. Okay, let's go ahead and let's do this. We're going to create a debugger reference here to step through this. If you haven't learned how to use the debugger yet, I highly recommend it, because this will help you as you're stepping through your code. You can actually look at the values in advance without wondering what they are after the program runs. So when you're doing that, put your breakpoints. You're going to click just a little bit to the right of the number, and it'll create just a red circle there for your breakpoint. Right click on the run method for the main and select debug. Okay. So system out print line, opening the file. We can see the arguments here. I'm going to go ahead and click next. Right now it's file byte stream is null because we haven't initialized it yet. So we're going to click next. And I believe an exception occurred. It did. So if we look at the exception, it says file not found. Num file, no such file exists. So let's take a look at what we have so far. Num file.txt. So let's do this. pwd. I'm going to get the exact location where this thing is at. Okay. Go back to debug, console, and run it again. Okay. And file not found. Why is it not finding it? Let's see here.
It says in the comments that it needs to contain 2 integers. And like in the comments for the code.
Yeah, no, it contains the numbers.
Yeah.
Didn't you name it .text? Because isn't that already a text file? So essentially it's numfile.txt.text.
I'm on a Mac, and if you were to actually look at this through the terminal, let's see, ls-la source, you can see that it's, yeah. I know what you're talking about, because in Windows, Notepad, it'll do that to you. If you try to name something different, it appends, yeah. Okay. File.
It says it shouldn't be outside of the source folder. just in 7 examples, because it's not included there in the error.
Say again?
Like the num.file.txt shouldn't be just in the examples folder, not in the source folder. If you look at the error, it doesn't mention the source folder in the exception. Like at the end, it doesn't mention the source.
Ah, it doesn't. Good catch. Okay. So, good catch. There we go. Debug it again. Okay. Thank you, Clayton. All right, so now we have the file, and there's the path for it. And we're adding the file input stream, which is this object here, right? We're going to assign it inside of the instantiated scanner. So we'll go ahead and do that. And now here's the scanner object. And we can see internally there's a buffer created, right? This is the buffer I was telling you about. It's basically just an array. And it's storing that data in there. All right. It's giving us a lot of details in here. These are properties off of the scanner class that you can look at. Let's go ahead and click Next. And we're going to call nfs.nextInt. And you might see an issue here. Do you see that? What do you see? Break line, new character, right?
Yeah.
But what it's done in reading next, it's actually pulled that value. So far, it's read it right. And then there's our second one. So it used the new line character to go to the next line and pull the next value. Okay? So it's printing those out, file 1 number and file 2 number. And then now we're going to add those two together and print it out. And then closing the file. Now this is important. Anytime you open a file, you have to close it. Maybe you've been in Windows and you go to do something and it says, oh, I'm sorry, you can't do that. And you're like, why? Right? And it's because there's a particular file opened and you're stuck until you actually close that file. Windows won't let you go forward. In Linux and in other systems, it's a little bit more forgiving. But if you do not close the file byte stream here, it will generate errors, especially if you try to read it again. So the rule is you open it, you do the processing to it, and then you close it. And then if you need to do something again, you open it, do the processing for it, and then you close it. Okay? So now we close the class, and that's it. Now we're done. So let's go to the console, and we can see that the number 1, 2, 3, 4, 5, 1, 2, 3, 3, 4, 5, 6, 7, 8, 9, yeah, whatever. And then we add those together, and then we close the file. Now, similarly, you can actually write back to this file. So you can read from it, and then you can write to it. But when you're going to write, you have to open up a new file input stream. You have to open up a file output stream, not an input stream. And you're going to write to a location instead of reading from. That is the file input stream. And I'm not sure if I had that in my, no, that's the last one. Okay. This really does set the beginnings though. So say in your future projects, say you want to store the data of maybe the game you wrote recently. You could store the data of your game now in a text file. You could update that text file and store all types of details. Maybe you want to create a grocery list, right? You could store those items in the grocery list, right? There's all different types of things that you can do now that you can write to files. I would prefer in this class that we actually would have the opportunity to connect to a database because that's one of the other things that you can do in Java using the Java database connection library. How many of you have taken your database course so far? Is anyone? Yeah. So in Java, you can create web pages with Java. You can connect to databases with Java. You can do all types of very interesting things. You can read files, modify files, and you can even compile in Java down to native code, and you can run it without using a JVM. So you can actually write your code for a Mac, or you can write it for Windows or Linux or whatever, and they're super fast. Guys, that is it for today. If you have any questions, I'll be here for another 5 minutes or so, 5-10 minutes. Otherwise, reach out to me this week if you have any questions. Again, please, 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 if you have any assignments that you're behind on and you want to get caught up on, please send me an email telling me which ones it is, and I can make sure that they're open back up for you again. All right? Okay, y'all have a good week.